I'm going to talk about C++ 20 modules, and I'm going to guess that most of the people present here have either heard of C++, I hope, and possibly on modules. Um, I've been hesitant giving a talk like this because although these modules have been standardized since 2020, they have a hard time actually working in all aspects that you would want them. And there's still rough edges, but I think it's a good point right now to, if you haven't, to start playing with them, to see what they can do, and to see, to be able to follow sort of the developments in newer compilers and newer build systems. What I have in mind to talk about today. First of all, what's the point of these modules? Why do we even bother with them? What did we do before C++ 20? Did we not have modules? We did have modules to some extent, but we had to do them in a different way. And that different way isn't exactly suitable for C++. We'll see why that is. And so that's what these C++20 modules are supposed to solve. In case you're not aware, the C++ language has a standard. It is updated every 3 years now. And so the latest one is from 2023. And it has some updates for how the module is supposed to work. But most of what I'm talking about, not exclusively, but most of it is C++20. So that is a standard that is almost 4 years old. So you would imagine that all of that must now be in compilers and in build systems. And that's not quite true. This is a tricky subject. And so one of the reasons why it's so tricky, it will hopefully become clear in this talk. But above all, since I want to be able to play around with these modules, I'm going to show you sort of a show and tell kind of thing of how you can make these work with current compilers. And I'm going to focus on two that I used myself, G++ and Clang, or Clang++. And the Intel compilers, the newer ones, are also based on Clang, so a lot of that probably translates to that. But everything is a little bit different depending on the compiler you're using, and so it's hard to be exhaustive in this field. But I'm hoping that you'll get a flavor for all of the different bits and pieces that you have to get right to do this, and also why it's worthwhile. So let's talk about what a module is. So in the abstract, a module is something that implements a specific functionality. It could be file writing, it could be performing a Fourier transform, it could be doing a machine learning task. One thing that it does and that it implements, but that doesn't try to do anything else. So it's self-contained, it can do those things without needing other bits of your program. And it has a well-defined interface to other codes. And this is a design principle. Most codes are fairly large, especially scientific codes. They have many aspects, and if you didn't have modules, if you didn't split it up in a sensible way, in a way that those parts can only communicate with one another in specific interfaces, then basically you'll go mad. And so that's what a module is. A module is a part of a program that has an interface to the rest of the program. And because it's now a well-defined interface, that can also be the start of what people call a library. So that's a piece of code that you might not even have the source code, but you have the compiled code, and there is an interface so that you can use that without having to compile it and without having to maintain it. But the module itself is just a separate, self-contained piece of code or software that can interface with your code. So the advantages are, first of all, that it's more manageable. If every piece of your code does just one thing, if something goes wrong with that one thing, you just have to fix that one thing. And so there's less guesswork if something goes wrong. It's easier to change things. If you want to change the output format, for instance, and you had an output module, that's the only spot where you have to look. You can test those also separately. So good software development means that you have modules that you test. You have a test suite. You can have one per module, And so if something, and so as you're developing, you can test just whether your module is still working without having to run a whole code, and if something goes wrong, having to guess which module was diversion. It also allows for reuse. So once you have your code, once you have your module and you want to use it in other code, it's much easier, because if the interface is well defined and doesn't allow you to go into the implementation, there should be no side effect. So you can just use that code and it does the same thing as it did in your original code. If done well, although this is tricky, it can also allow for parallel compilation. So if you have different bits of the code that are all in different modules and they don't depend on one another, then when you're compiling, you can compile them at the same time, and that can speed up compilation quite a bit. So that's great. So there's advantages to doing this, regardless on how you do it. And so modular programming is a sort of an underlining skill that you should have as a software developer, whether it's scientific software or elsewhere. A last point that is important, particularly for the manageability. Your other code doesn't have to know anything about the implementation, and it shouldn't be able to access that either. That way, the responsibility for that piece of the code is just for that module, and so that enables all the other advantages in a sense. Okay, so I'm not just an analyst at SciNet. I also teach a graduate course at the University of Toronto in scientific computing, and part of it is teaching the graduate students modular programming. This is one of the reasons I'm interested in this topic, because we're using C++ in that course, and you would think that since 2020 we'll just use these newer features, and we can't quite yet, but we can do modular programming. And so what have we done? What are we doing now? And why is that still a decent approach? So what you have to do in C++ to use this idea of modules is to use header files and source files. And that comes way back from its predecessor, the C language, which is full of header files and source files. And so we'll look at that briefly just to give a sense of where this all comes from and how you would do it, even if you didn't have modules, because you do have modules that way. So imagine we have this piece of code. This is a code that computes the fifth root of 0.01024. That the answer is actually 0.4. We don't really care how it does that, but we have a function here called fifth root. It takes a single double precision number and it returns another one that should be the square root, and it computes it somehow in those dot dot dots. So I'm not specifying that because it's not a point, but imagine that it does the right thing and it returns the result. Now, being able to compute the fifth root is very useful. So, oh, by the way, if we want to compile it, I'm going to pretend that we're all on a Linux-like machine or Unix-like machine. Could be a Mac, could be a terminal, even in anywhere, and that there's a compiler that's called $CXX for now. We will be more specific later. But the way you would compile it, you should give the source file name and the output that you want it to be written into, and you compile it, and then once you run it, it should give the answer. So that's 0.4. So this program works. There's nothing wrong with it. It gives you the right answer. Now everybody knows it's 0.4. It's done. But suppose that this fifth root function is really useful, and we want to be able to use it, or it's more complicated and part of a bigger software application that we want to separate it out as a module. Okay, well, this is what you would. So we're going to try and do that. And we want it in a way that the user of the function, which is this main function in this case, doesn't have any access, doesn't see the interior of the function. The implementation should be hidden, but it should be able to call it. So for that, we need, instead of this one file, we need 3 files. Here are the 3 files. We need one file that's the interface file, and it basically just defines the function. So here's the function again, but it doesn't have the body of the function. It just this declares that it exists. There's some extra extra code here to make sure that if we use this interface more than once, we don't doubly define anything. And for some entities, doubly defining things is bad. So we don't want that. And that's where these if defines come in. They make sure that if the first time you import this interface, it's defined, and the second time it's skipped. This just defines that it is existing. This function exists, and that's enough for us to use it in the calc fifth root application by including the file. So we're including the file and we're writing it out. But we still need to know at some point where how to do this fifth root stuff, and that's in the implementation file. So that's here in the CPP file, and it just has both the function and its body here. So because the header file is included in C and C++, including a file is literal. It's just basically pasting whatever is here into the include. The same happens with the IO stream. The IO stream is the C++ library for input-output of text to the console mostly. But that is literally put in there. That's why you don't want to have it in there twice. But that means if it's included and it only has the interface, only has the definition, then I can change the implementation if I needed to without having to even recompile the main function. So it's a little bit in the corner, but I hope you can see it. So the way to compile it then is you have to compile both CPP files and then link them together. So if you want to compile them and not try to create an application, for at least a lot of compilers, that's the -c flag. So that means compile it. And at the end, we link them together. So when I'm compiling it, this can be done independently for the two .cpp files. So that could be done in parallel. Oh, sorry. Could be done in parallel. But then when it's linking, that's when it realizes that this particular piece of code needs a function that's called fifth root and that its implementation is in the other object file. So that's the linker's job to do. So that's the standard way that both C and C++ work. And this is modular. This is a module. We won't call it a module soon anymore because there's something else that's called modules. But this is a module. And the nice thing about this that is still kind of nice now is that the same mechanism works for, say, if you have C modules. And so a lot of software is still written in C, and you can use that in the same way as your C++ stuff. So it sort of makes it uniform. By the way, there's going to be a lot of explicit compilation lines in this talk. I'm not using a build system, I'm not using an IDE, I'm not using Visual Studio. I'm using command line for the reason that that's much simpler. It's much simpler. Don't want to be building with CMake or something because we need to understand what's going on. The support isn't at a level where if you don't know at least what's supposed to happen, you won't be able to make your favorite IDE do this yet. Things will progress, but that is. So this seems low level maybe to type in the commands yourself. You could, if you like make files, I like make files. If you like make files, you could put those in the make file. But again, what you have to put in there depends a lot on the compiler. So to be explicit, we're not doing any build system. We're just doing compilation commands. And at the end of the day, you will want to make sure that whatever build system you use, it generates that line. And that is not trivial. So that's why I'm not doing it. Okay, so this is a nice mechanism. Why did it need to be improved? Why did it need to have changed for C++ and specifically for C? It kind of works quite nicely. There's a few rough edges there too, but there's a few things specifically for C++ that make this not great. First is that you require what's called a preprocessor. So these pound if define functions or pound include, that's a preprocessor that reads those and interprets those and executes them. The include file, the include statement itself, literally includes whatever is in that file. So there's no checking. It's a separate language, and that language is different from C++, so it has side effects. It behaves differently. It just makes it harder to keep track of things. So the preprocessor is in a sense bad. It's not good practice unless you really need to. They don't check types. They have their own syntax. They generate code. Um, it's very easy to go right. So even when you do use the old style module system, so header files, you only use the preprocessor for very specific things like making sure you include only once and to include the files themselves. And other things like macros, constants, there are perfectly good C++ replacements for those, and you do not have to use the processor for that. So there's this trend to use this less and less to become more, let's say, self-contained in the C++ language, and that would be better. It is also error prone because there's things that you have to put in this header file that you'd rather not expose that are somehow related to the interface. And so it's really tricky to properly separate the interface from the implementation, and it's easy to make a mistake. So the first guess might be to just put everything that you might need in the header file, but now you could have side effects. And so that makes it error prone. And finally, C++ has this thing called templates. So template functions, template classes are actually not functions and classes. They have in the simplest case, type parameters. So you could have a function that works on any type of variable, but it doesn't. It's not a function that works on any type. It would be a function that is generated for every type. So you have a new type that you call with that function. It now generates the definition of that function. That means that the interface, the header file, has to include the code for that template, because otherwise, when it's used, only when it's used does the function get generated and then has to be compiled. And so there's no separate compilation that is possible. So the only way you can compile it is if you know the code that is necessary to implement it. And so with templates, this separation of an interface and an implementation is broken. You can define classes with private parts, but you can do very nasty tricks where you can still see those and can have side effects. So the separation doesn't work for templates. So that's another reason why you'd want something better for C++. It is not that you can't say what you would want to show to your user code and what you don't want to show. That is fairly clear. It's just that there's no way to not also include all of the implementation. So for these reasons, getting rid of the preprocessor, making it less error prone, and making sure templates can actually be in a module without mixing interface and implementation, people came up with a newer standard. So that is the C++ 20 modules. And so one of the things is you don't need a preprocessor. You can still use it. That unfortunately has to be a demand, and that's one of the reasons this is actually tricky, having the old way cooperate with the new way. But for pure C++ 20 modules, we'll see we don't need these. We don't need any preprocessor stuff anymore. It becomes less error prone in the sense that you have to say exactly what gets shown to the user code. And so you export particular parts of your module, and anything that you do not export is just not reachable. And so it's better because the default is to hide things in a sense. You have to be very explicit what is exported. And templates are fine too. You can actually control what's visible, so that way you can say, okay, I do want to export or I don't want to export, but if you export the definition of a template, that doesn't mean that you suddenly can mess around with the functions. Don't have really time to show that here because templates are their own sort of big topic, but it does solve the interface implementation visibility issue. All right, so I'm going to show a few examples. Let's see if there's any questions so far.
Not so far.
Great, thanks. Okay, I'm going to look at the ideal situation first and then see how close we can get to that. So in an ideal world, we are living in C++23, which is the standard that was adopted last year or really the beginning of this year. And so in an ideal world, all of the compilers, all of the build systems would know about it and be happy. And so one of the things you would get when the full standard is implemented is that the way you would write an hello world program in C++ is now actually different. So it used to be like this, right? The old style, well, I'm going to call it old style now. You include the IO stream, you have your int main, and you stream hello world into std out, and you end it with std endl to end the line, and that's it. And you can just compile it with G++, for instance, and just give the name of the file. But this uses the include statement, so that is using the preprocessor right there, and so this is not modular. According to C++23, this is one way you can actually write it now. You can import std. So you probably know IOStream and a whole bunch of other header files are in the standard template library or the standard library for C++. And if you need a little piece of them, you have to include them separately. In C++23, there's supposed to be a module called std, and you can import it. So there's no pound sign here that is indicative of the fact that this is not a preprocessor. We're just saying we want to use this module. And one of the things that's in the module is a print line function. So std cout is going away, and, well, not going away, it's going to be deprecated, and print line is a much nicer way to do it. It is shorter. It is a template, so you'll be able to pass it other variables as well. So if you want an integer, that's fine. So it works as versatile as the streaming operators, but it's a function. Okay. Now that's nice. There's no processor lines. There's one std module, so you don't have to think anymore about which header things come from. This is going to be brilliant, but I do say it's going to be, because we're not there yet. To compile, the first one is just compilation with the name of the file and an output file, and you run it and you get hello world. In the second case, there's probably a flag you have to give to your compiler to say, hey, use the C++23 standard, and then other than that, it should be the same. This is how it should be. This is not how it is. This is how it should be, and hopefully at some point we'll get there. We will see why and how it's not quite there yet. So that's even just hello world. That's the simplest case to get rid of the preprocessor, to get rid of header files. How about this modularization? So I showed you this example of the fifth root on the left here. So here are the three files again, and so it goes a little bit off of the slide, but I put the compilation lines there as well. So we've got our interface file, we have our implementation file, and we have our user file. With modules, this actually gets to be, again, quite a bit simpler. And you can always split up things in more than one file, but there's only need for one file for the module. So it's called fifth root CPP, so it replaces the old CPP here. And it says it's a module. It gives it a name, doesn't have to be the same as the file name, but in this case I chose it to be. And I want this module to be importable from other files, then I have to say that I can export it. So export module fifth root defines this is a module that can be imported. It needs some other stuff. It needs, for instance, the CMath library, and I'm importing that rather than including that. And that makes this what's called a header unit, and we'll get to header units in a little while. But I need CMath because apparently the implementation of fifth root needs CMath. Rather than including it, I import it. I'm exporting the function, but this doesn't mean I'm exporting the body of the function. This is just this is, in a sense, we're automatically generating a header file. We're not, but it's as if we're generating a header file that has fifth root in it. So it has a dual purpose. It is the what they call the primary module interface, And so this says, okay, there is a fifth root and there is a module. You can have other functions in here that might be used by the function that are not exported, just as you could have other functions in the implementation that aren't present in the header file. But rather than having to copy things around, you can just have one file. And what you want to be importable from another source file, you have to just indicate with the export. There's a lot more to it. There is a whole, but I'm just going to show you the basics and then trying to get that to work. Then here's how we use it. So this is our user code. We're importing IOStream because we're still using cout here. And I'm importing the module by its name, import fifth root. And so this doesn't include anything. This just makes the fifth root function available for me to use. If there's any other trickery going on in the .cpp file to make things run, if it included rather than imported something, none of that makes it into the import statement. So if I had included CMath instead of importing it and supposing that that would have worked, that might have defined a whole bunch of stuff that comes from CMath. I don't have access to CMath here. I just have access to fifth root. That's the only thing that was exported. And that is very different, for instance, from including, if I included a header file that would have included CMath, I would have all of those in there. So this is neater. This is neater in both cases, and it's tidier and it's nice. It's shorter. Compilation should be something like compile the module. You might have to say that it's a module, so there's some sort of flag to say, hey, this is a module. And then I have to also compile my my code here to an object file, and then I link it together. We'll see that oftentimes, actually naturally, the compilation of the module will also produce an object file, so that would have to be in the link stage as well. But that's the idea. So nice and
Just there is a question about the scope of the export module directive.
Okay, hold on a second. Yeah. So export module actually says that this is a module file that can be imported. So the scope is it. This is an indication that the whole file is a module file, and that this module file defines the fifth root. So there's no scoping here in that this fifth root isn't suddenly available inside the fifth root.cpp file. I hope that answers your question. The scope, on the other hand, of the import statement means that the only thing that is now reachable once I've imported it is what was exported by the file. So so anything after this module command is part of the module. So if you want to see it that way, the scope is everything below it. Everything below it is part of the module. There's no end module, and then you start a new module. That's no. This is a file. It is the whole thing is a module as soon as it starts somewhere with export module fifth root. If I put something in front of it, I'm not sure if it's even defined what that is. If there's no other module command there, a module statement there. Okay, so that's great, fantastic. Use this. There's modules now. Things you don't have to have header files if you don't really need them for small modules, and preprocessor out the window. Nice, but most of this doesn't really work. Parts of it might work sometimes not. It depends on the version of the compiler a lot. It depends on exactly how you use things. There's a lot of tricky corners. So what I've tried with this talk in particular is to show you a few ways that do work and that work pretty much as advertised. You just have to know how to compile it. That's a big just, but you do have to know. So why is this so hard? Why is it not just like as soon as the standard came out, compilers jumped on it and now we're all just using modules? One of the main reasons is that you now need two things to come out of a compilation of a module file. You need the object file, so that's the same as before. And you need a second file which takes the role of the header file, but is a lot more than that. And it's called a binary module interface. BMI is its abbreviation. It doesn't even have to be binary, just the name stuck, I guess. It has not just the definitions of your files and but it also has, say, must somehow have the definitions of your templates, because if they're used, then they have to be generated. So there's a lot of stuff that can go into those, but it's a separate file. So every compilation now contains two. Some modules might need other modules, and so that introduces dependencies. And different from header files, where they're kind of static, right? They're not generated. The BMIs are generated from the CPP file for that module. The BMIs have to be stored somewhere. So you might think, well, you just put it right next to the object file, and that would be reasonable. And that's not how it goes. And one of the reasons that it's not that trivial either is that this BMI will change depending on your compiler, depending on the compiler version, depending on the compiler flags, depending on. So you can compile with C++20, and that gives you a different BMI than with C++23. They are not compatible. So there's a lot of incompatibilities. So the compiler version, compiler flag dependent objects. One of the reasons that is so, because it doesn't have to be that varying, is that these are built upon older architectures or older technologies called compiled header files. So you can pre-compile header files. And so what that does is it rather than parsing the header files again, you just basically do a memory dump of whatever the compiler has after the processing has stopped, and you dump that. And so when you read it in, you just read it in basically as binary. That's why it's binary. But it is also why it depends so much per compiler. So that is a disadvantage. Header files can be fairly static. They can use tricks with precompiler constants and if statements and stuff that are tricky, but have a functionality to them. The BMIs have to be generated every time something changes. And yeah. And then the question is, what do we do with code that already exists, that is in header slash implementation file format? So what do we do with legacy code? Can we make that happen? And even worse, all of the standard library that comes with C++ is header files. And they have to be header files because most of it is templates, and templates need header files to be. So can we, so the examples I showed pretended like everything was fine. If you had a CMath header file, you can now use a CMath module just by doing import instead of pound include. But there's technical issues with that because a lot of those header files do use, let's call it tricky code that depends on a preprocessor. So this makes it hard. There's dependencies that are introduced. There's more compilation that has to happen. There's more files to keep track of. And then because it's built for most compilers on pre-existing technology, that technology was always dependent, specific to the compiler. So Clang did it one way. In fact, they had some sort of modules for a long time. They're not compatible with these guys. C++ does it one way. Visual Studio or Visual C++ does it another way. Everybody did it a different way. That's why it's so hard for this to automate. So let's see what we can do now, though. Let's pretend there are no issues, or let's just go ahead, jump right in, try it, and just fix whatever isn't working. Yeah. So I'm going to focus on two examples, the ones that I already showed. Hello World, which just involves trying to use standard libraries as modules, which I just mentioned is a bit of an issue. And then the modular code that calculates the fifth root. So that's where we have a module of our own that we want to compile and link and so on. And I'm choosing compilers, one of the versions here is wrong, that I know are available on the general purpose clusters in the Alliance, as well as on Niagara. So G++12 and actually Clang 17. There are modules for that. If you log into any of the clusters now, I think G++12 is loaded by default now. You can do module load clang, and you'll get clang 17. I don't have access to Visual C++, unfortunately. In fact, I don't even know if I would have time to check everything, but honesty does make me have to say that the Microsoft compilers are way ahead of supporting this kind of stuff and have been for a while, and supporting C++ modules. I guess it helps if your build system is also yours, but that's a lot of things might work there that don't quite work yet for C++ and Clang. These are not the latest versions of the compilers. They're G++13, Clang. I'm not sure if it's up to 19, but it's getting there. And so they will have maybe slight improvements. For the most part, what I'm showing here will still work, I think, in newer versions, but your mileage might vary. Okay, so our first compilation that we want to do is our Hello World. So here's Hello World again. We import std. The whole std module gets there. That includes our print line, and it will print the line Hello World. So we start compiling that. Well, first let's make sure that we have a compiler and what the version is. So this is indeed version 12.3. Okay, so G++ needs a flag to say that we want the C++23 standard. This is how it goes, and then our source file and our executable that we want to create. So let's see. And no. So the first thing that it says is that import does not name a type. That's nonsense. Import doesn't have to name a type. Import is a statement in C++23, and it is just very strange, but also telling that just giving this flag does not switch on all of the C++23 language even. And so it says that C++20 import is only available if you also give another flag, and the flag is actually -f modules ts. And then, since that didn't work, there's no point looking at the other errors. The first error is always the most important error. So let's fix that. It sort of gave us an idea of what the flag should be. It should be -f modules -ts. And does it work now? And no, it doesn't work. Why does it not work? It now complains about std errors, failed to read a compiled module, no such file of directory. Compiled module file is in GCM. So it has a whole bunch of stuff to say here. But in the end of the day, the fact that it can't find std just means that our compiler doesn't have an std module. Which again is kind of funny because it's part of the C++23 standard, but and this has been going on for a while, compilers do not consider the libraries as being necessary to say that they follow the language standard. And so it's a bit of a pet peeve of mine. I would say the standard contains both the language and the library, and so if you say that it's C++23, it should be C++23, or there should be another flag. Compilers do not agree with me, and they say, well, we might have the language okay, but we don't have all the libraries, and so they don't have the std. Hopefully at some point they will, because it will make our life a lot easier. At this point they don't. So we have to take a step back. This is not our Hello World program, and almost no compilers will support this as the Hello World program yet. And so we're going to take a step back, and we're going to use the print header. So the print header is also part of C++23, and it is actually what gives us the print line function. And so that's so we will try to import print and see if it goes then. And no, still no luck. Print, no such file of directory, and it's the same problem. If this was truly C++23 compatible, then there would be a print library, because C++23 standard says that there should be such a library, but there isn't. So print doesn't work. Let's try our old IO stream. Can we import IO stream? So the old Hello World still had include, we import, but once we've imported, can we use it then? So same compilation line, and still not. Because I'm using the software stack, the Compute Canada software stack here, the lines, the paths are kind of long. So I'm going to abbreviate this. I'm going to call CMFS Soft Compute Canada Gen 2 2020, etc. Just X. This is a shorthand. This won't appear on the terminal. If you have your own compiler installed, it probably says more something like /user/ lib or something like that. Something shorter. So now that we can read a little bit better, the error is that it failed to read a compiled module. No such file. So again, we have an issue, but there's something we can do now because, okay, we know IOStream exists because we did found include, it would work. So it exists, but it says there's no compiled module file. And it says what it is, or really what it should be. It should live in this directory here. So we have to create this. This is not automatic. Doesn't come with a compiler. We have to create. This is the BMI. So it's called as GCM because all compilers choose different extensions for pretty much everything to do with modules. But this is this BMI that I was talking about. There is no BMI, no binary module interface for even the standard headers that come with the compiler. We have to create it. And that makes sense because if we have different flags, we have to recreate it anyway. So there's no real good way to do it otherwise. So imports must be built. So we haven't built anything for IOStream. It doesn't exist. Another thing that is kind of funny though is that remember X is a abbreviation for this long path, but the GCM cache is going to live in the current directory. So all these BMIs, since they are generating by the project, are in the project directory, and they have but they inherit the directory tree structure from where the actual IOStream is, which is right in here. So that's why it gets a little long and it's a little bit funny, but that's what it wants. So what we have found some issues that we're going to solve. We need this special flag, modules TS. That's fine, we can do that. There's no std module or print header. The print header actually will come with G++14. If you like compiling from untested code, you can git clone their repo and play with that. It does work, but we'd have the same issue where we still have to first compile the BMI. So these headers have to be compiled. And when you compile headers, those are a special kind of module called a header unit. They have a lot of issues. People don't like them, but there are a way to get the headers that we have and to make them into importable modules. Okay. Let's try that. So what we need to do before we can do Hello World is to compile our header unit. In this case, the IOStream header unit from header files. And so we're going to try that. So again, I'm using the abbreviation so that this long path is there. I'm going to try to compile this. And we know that if we have to compile for modules, we have to tell us the standard, 23 standard, and the modules TS. And then I'm just giving it a file name of this header file because that's what I want to compile. And it doesn't like that. And it doesn't like that because even though compilers choose their own extensions, and this is a header file that comes to G++, you would think that it knows it's a header file, but no, it actually thinks it's a linker script. Because if there's no extension, then apparently G++ thinks it's a linker script, and that's not what it is. What it is a header file. So it turns out there's a flag that you can give to tell it what the language is of this file, and the language is C++, but it's a specific C++, it's a system header. So this is a bit of extra flag you have to give to G++ to tell it, hey, this is what this is. Okay, does that work? And this is from all the different error messages that we're going to see, this is the strangest one. It says there's no such file or directory. And remember, $x really is, does this exist? Yes, ALS it, and it exists. It's right here. The output will not have $x. Right? I'm abbreviating here because you wouldn't see, but it actually exists. It has a non-zero. There's nothing wrong with this file. It does exist. What is odd here is that it turns out, and this is just something you kind of have to try, Um, when it's a system header, G++ now becomes smart and says, I'm going to prepend this for you. So what it's actually looking for is $x IOStream, and that does not exist. So how do we get around that? We just get rid of the $x altogether, which is kind of nice because we don't want to have to specify where these live because it depends on the compiler. So this is the compilation command you need. Compile for modules for 23. These are system headers. This is the name of the header file, and nothing is returned, which means success because it's Linux, and in Linux, silence is golden. Now, nothing happened, but we wanted something to happen. What did we want to happen? We wanted to get this BMI or the GCM in this case. So let's find it. Usually, when you create a file from another file, the names are related. So I'm just doing a find for anything that has IOStream in it from this directory, and there it is. In the subdirectory gcm.cache, and in the nested subdirectory that this X represents, at the end of it is iostream.gcm. This is our BMI. We have a BMI. Okay, it's in a funny directory. It's not easy to change what the name of the directory would be or where it goes. When it's not easy, it's probably best to try and stick with these defaults. Okay, we have a BMI. Can we compile? Let's try it. Here's our hello world. I rewrote the compilation for the header unit, and then here's the compilation for our hello world, and yes. So G++ does know where it stored this BMI, and it will import it in the right spot, and it will do everything. So had we had a print header or had we had an STD module, then this would have worked with that as well. So this is going to generalize for the future as well. But this is so yes, we can have hello world. It's not exactly as pretty as we might want it, but it does have a header unit that we compiled, and then once that's compiled, once that exists, we can import it and use it in our code. Questions?
Nothing at the moment.
Okay, thanks.
Actually, I have a question.
Yeah, go ahead.
So the C++ headers files are interrelated in complex ways, but one depends on another.
Mhm.
So when you're building, for example, this IOStream header, you are actually including some other subheaders, which could have also been built separately if you wanted them.
Yeah. So this and so you had yeah. So
Yeah.
that is an issue, and it's a big issue. So if you tried to to uh, create header files, header units for all of the standard um, header files, it wouldn't work. There's some that just depend in funny ways, and then the order in which you do it depends on whether it works. Now, it doesn't have to be that way. It's because those header files haven't been adapted to let's say guard against that. Because when you create a header unit, whatever happens in so when I'm importing this, whatever happens in the IO stream or whatever happened before shouldn't influence the module, but it's a big shouldn't at the moment anyway. So yes, if you've got more header files and they are interdependent, this can sometimes just basically not work. And what you'll get are what are called internal compiler errors. The nice acronym is ICE. And so ICE errors, you cannot solve them. That means you have to wait for the next generation or the next version of your compiler. And that is so individual ones I've not had an issue with. So if you need one or two or maybe three, we'll see two in at the end. It works. These for G++. But yeah, your mileage definitely varies if you wanted to use all of them, which is probably also why there is no STD module yet, because you would need all of them. And so there's work to be done there.
There's another question in the chat about optimization.
Right. So optimization, it depends a little bit, I think, but there's still an object file that is generated from the module. Not here because these were header files. They never would have had an object file. But other modules will have an object file, and there's probably a certain amount of compatibility, and you just say when you compile that module what your optimization would be. But other things, especially if you use preprocessor constants to tune how your header files work, those, when they change, you have to recompile your BMIs. So there is definitely a larger amount of dependencies in these that is hard to keep track of. Another reason why build systems have such a tough time getting getting this to support. Forget about knowing exactly which flags there are, which you could automate that, right? You could say, okay, if it's G++, use the F modules TC. If it's something else, use another flag. But that is a very tricky situation. Yeah. It's also why you compile your GCMs yourself in the build system. Sorry, in the build directory. Okay, so I'm going to go quicker through how it goes in Clang because it's very similar, but there's differences. So here's Clang. I module loaded Clang, and now it's Clang 17. I'm going to try first the same thing. Does it work with import std? No, same reason. Std doesn't, the module doesn't come with its compiler yet. Let's try the print library. Does that work? Nope, print can't find it either. That shouldn't be surprising, but no, that's how it is. So back to our IOStream. IOStream, does that work? Not quite, but it gives the same answer. It says I can't import it because I don't know that it's a header unit. And then, yeah. So how do we compile this header unit in this case? That is the question, right? So it's different, but not a lot of different. We don't need a special flag. That is funny, but okay, that's actually a good thing. There's no std module, there's no print header, there's no IOStream header unit. We still have to compile it. Also, if you look carefully at the error message, you see that the header file that we have to compile is the IOStream from G++. So Clang, at least if you just install it without anything else, will use the C++ library that comes with G++, which is a little bit funny. You could call it a cop-out, but I guess it's an optimization. That's okay, but that's also why there's no print header, because our G++ didn't have a print header. That's basically what's happening here. So we have to compile this header file that is in this long path, which was X. So here's X. We're going to compile that. We're going to try it. So we're just going to give it to Clang++, set the standard, and see where it goes. And it says, I don't know what that is. Again, same issue. Is this a linker script? At one point, Clang was essentially a drop-in replacement for GCC or G++. That's not quite the case, but a lot of the errors are very similar. So that's why this is so similar. So the same flag works, -x C++ system header, to tell the compiler, hey, this is a system header, please compile it for me. And then it does it, but it gives a warning. It says, hey, this header file tells me that it's really for GCC, but I'm going to ignore that. So it actually worked, but I don't like this. Like, if I know why a warning happens, I guess we can suppress it. So this is how you do that. Just tell it exactly what warning you got, and you don't want them. So now it works without like extra output. And did it work? Well, again, let's see, what did it generate? What did it really make? And it made something called PCM. This PCM is in the current directory, so that's very different from our G++ wants to store them. And it's called iostream.pcm, not GCM. I guess it's a good thing, because then you can't accidentally have GCC read in a Clang precompiled module. That's actually what PCM stands for. Anyway, we have our BMI. This is the BMI for Clang. Can we now compile hello world? So let's see. So X is defined again. We compiled our header. Oh, I will note that we had to, in this case, give the exact path of the header file, because this is not a header file of Clang, it's a header file of G++, so full path. We have our IOStream, and I'm going to compile header hello world. That should work, and it doesn't. Why does it not work? It still doesn't know anything about IOStream. So Clang is a little bit more explicit, or you have to be more explicit, first of all, with the full path, but also it still doesn't know where it's stored this iostream.pcm. Just because it's the current directory doesn't do anything for it. I have to tell it that I want to use the module file iostream.pcm, and that's just how Clang currently does it. And so when we do that, it works, but it gives a warning because it says, hey, header units are experimental. And that's fine. So we don't like warnings that we know are there. We know it's experimental now. So I'm going to switch that off and we get our line. So we have a long line to just compile this code, making sure that the right PCM is loaded, but then it works. So you can make it work. Flags are different, locations of files are different, which would change how you would write a dependency graph, but in any case, hello world is success. This was my, I think, literal expression when I first tried this, because you really have to be a little bit resilient against initial failure to get this to work. And at some point, there might be things that just do not work, but hello world should work, and it works. Good. Now, let's go to the actual purpose, and I'll just, I know we don't have a lot of time, but this is what they're for. Can we make modules? So here's our module. Here are 2 files. So you would think you can just compile things. Here's our header files that we have to compile. Now I note, because we've learned a few things just now, that I'm importing CMath, so that's a header unit. That won't exist yet, so I better compile it. So I'm not just compiling iostream, back to G++, by the way. I'm also compiling CMath, because I'm thinking ahead of time. Then I'm compiling my, my 5th root here. So that's the module itself. That will produce 2 files. It will produce the BMI, which is called a GCM in this case, but also an object file, because this has actual code in it. So that is a 2-file generation. And then I'm compiling my main function here, and I'm linking them together. And it does work. So yes, as long as you make sure that these header units are working, it's really not that, it actually kind of works nicely. Success. We've generated quite a few artifacts though. So we have our CPP files, we have our object files, we have the GCMs for our O module, which just live in the main GCM cache. We have the stuff that comes from the compiler, which has this long path that I abbreviated by X. So there's a whole bunch of stuff. And if something changes, we have to rebuild those. But that's how it works. Okay, a few more remarks. Oh, sorry, I pressed my button a bit much. So we need BMIs. That's what the GCM and PCM files are. Other compilers will call them differently, but those are all, then they're not compatible with one another. So, but those are the ones you need. When you compile a module, you have 2 files. You have your object file and your BMI, except for header files, which don't have an object file, right? So except for header units. BMIs need to be compiled with the user code. So even if your header is there, even if you had another library already that had a header file, you want to wrap that into a module, you can, but you will have to compile those, and every time you change something, you have to recompile those. You cannot define macros. So if you love macros, modules are not your thing, because they don't escape the module file. So the export, whatever file says export module, yes, you can do preprocessed stuff in there, but whatever you define there doesn't make it out, which I think is a good thing. So if you need those tricks to get something to compile, at least it doesn't influence the user code. So that's a good thing. But if you needed macros, or then, yeah. Except for header units. So it turns out header units can define macros, and they do make it out of the module. I'm not quite sure why they did that. In any case, they did it. And so I guess the idea is that importing a header unit should be somehow equivalent to including it. I really don't know why, but anyways, that's an exception. And that's related to the question that was mentioned earlier. If header units need other headers or other header units, this can be very tricky, because if it uses a header unit that isn't compiled yet, then it will complain. But so the order of compilation can matter, and to make that work is, I think, one of the reasons that it is not all implemented yet. So it's a bit fragile. You need to know what flags to use, etc., which is at this stage, and people complain about it for a good reason. It's still sort of almost the best build system that you can do is one that is very explicit, and so makefiles are you can be very explicit. So makefiles, there's no issue making this work in a makefile, but you have to do a lot of things yourself. Where other build systems that find dependency trees and stuff have difficulties and have to catch up. But a lot of work is being done on this, so it will get there. It's just so that's why it's not bad to look at it, to try some things and make things work. Right. So these things are coming. They're just slower because of the technical difficulties. So the point of the talk today was just to get something to actually work. So we have a hello world that works. We have a module that can work. I would strongly suggest, if you can, don't try to mix and match header files and header units. That is almost certainly going to lead to compiler errors. And with not much. So if you can, do the whole thing. Just make it all modules, and then you have the best chance for things to work. So that's what I've tried here. I've definitely not shown all the difficulties. Dependencies are an issue. Header units have their give people a lot of headaches. Right? But at the same time, despite or maybe because of all those headaches, I'm glad somebody's thinking about them, because I really don't want to have to think about what the different flags are, how the dependency graph really works when I have BMIs, what happens if different headers or header units or different modules import. So this might be one of the reasons I will at some point properly learn CMake, because it will be able to do this for me. Is it there? No, not yet. But once they can do that work for you, that's a reason for a build system. I was not comprehensive here either. I'm not going to pretend that. There are some nice talks that I found that actually were helpful for me to understand better what modules are supposed to do, and then explain better what the framework is, how they're supposed to work, what the different parts of a module can be, why header units are an issue. So Andreas Weiss, Daniela Engers, and Daniel Russo, any of their talks are great, but these are a few that I picked out. So thank you for your attention. If there are further questions, I'm happy to answer those.